Ladies and gentlemen, welcome back to Lesson 6 in Group Theory. Group Theory is the course where we ask a lot of interesting questions and we try to come up with answers that make sense. The first question that we had in this course in Lesson 1 was, what if I had a set of elements and I had a single operation and I satisfied certain properties? What kind of construction can I have then? And the answer to that question was, we would have a group. Here in Lesson 6, we ask a similar question. What if I had the same set of elements, but instead of having one operation, I had two? In this case, I call this a field. And fields is the topic of the first discussion we will have. We will introduce fields, and we're going to be talking about finite fields, some of which are denoted by FQ. And I will explain that in a minute. And after the field discussion, we're going to be going back to some very interesting groups. We've already seen some interesting groups in Lesson 4, where we've seen dihedral groups, and Lesson 5, where we've seen symmetric groups. But here we're going to be talking about matrix groups and quaternion groups. Let us start with the definition of a field. A field is a set F with two operations, not one, like groups, two operations plus and multiplication, such that F with plus and F cross with multiplication are both abelian groups. I have also another property that multiplication is distributive over addition. Distributive, that means the same way it means in elementary school, A times B plus C is equal to A times B plus A times C for all the elements in the set. So in this definition, I have a couple of remarks. First of all, the Fx means simply F that is not zero. So all the non-zero elements in F. The second thing I want to mention is that abelian means commutative. Commutative, it means A times B is equal to B times A, or A plus B is equal to B plus A, depending on which operation you're taking. So it is important that with plus and with multiplication, we have abelian groups, and that the multiplication is distributive over addition. And then and only then we would have a field. Now that we have defined a field, let's have a look at some examples. We have the most basic examples being the set of rational numbers, the set of real numbers, and the set of complex numbers are all fields, with the operations, the usual addition and multiplication. For example, Q is a field because with addition, Q plus is an abelian group. It's an abelian group because it is associative, commutative, there is an identity element which is 0, and every element has an additive inverse. And now Q, X with multiplication is an abelian group as well, because multiplication is associative, commutative, there is a multiplicative identity which is 1, and for every element that is non-zero in Q, there exists an inverse. So for example, the element 2 multiplied by its inverse, a half, gives back the identity which is 1. This is not the case for Z. So Z, the integers, if we take the element 2 in Z, the multiplicative inverse of 2 does not exist. So there is no way for Z to be a field, even though Z is a group with addition. It is not a group with multiplication. You can verify yourself that the set of real numbers and the set of complex numbers are fields as an exercise. The last example of fields is Q adjoining the square root of 2. It is simply put all the elements of the form A plus B square root of 2, where A and B are rational numbers. And this is a subset of the real numbers. And this is in fact a group with the usual operations of plus and multiplication. The past few examples were examples of fields which were infinite. They had infinite amount of elements. Here, we will have what is called a finite field. So let's construct these finite fields. Consider the finite groups Z and Z with addition and Z and Z star with multiplication. So already these groups are finite groups. Now we have addition and multiplication. So we have two candidates for operations. We need to verify if these both form abelian groups. Well, what is Z and Z star? Z and Z star, if you remember from previous lessons, was all the residue classes A and Z and Z, such that the GCD of A and N is equal to 1. In other words, all the residue classes in which A is co-prime with N. So if we let N be a prime number, let's say N was equal to 5, then Z5Z star would contain all the non-zero elements in Z5Z. So it would contain 1, 2, 3, 4. Because all of these elements are co-prime to 5, which is prime, because prime numbers are the only numbers in which the only divisors are themselves and 1. So the only number that is divisible by 5 is a multiple of 5, which is 0 bar. But 0 bar, we do not need to include it because remember, in the definition of a field, we only need to include all the non-zero elements in the set. And here we have indeed included all the non-zero elements in Z5Z. So more generally speaking, if N is equal to P, a prime number, then ZPZ X or star, it is the same significance. It would be equal to 1, 2, 3, all the way to P minus 1. So all these residue classes, all the non-zero, so it is equal to Z, PZ without 0. And addition and multiplication are very nice operations that are associative, commutative. There are identities for a plus and multiplication, which are 0 and 1 respectively. There are multiplicative and additive inverses for both plus and multiplication. So in conclusion, we have satisfied all what we need to say that this is an abelian group and this is an abelian group, and we have that multiplication is distributive over addition. So in conclusion, ZPZ with the two operations is a finite field. Now that we have completed our discussion on fields, we can use fields to fill out matrices. So consider the set of matrices with entries in some field F. We define GL and F to be the set containing all the matrices A such that A is n by n, the dimensions are n by n. The coefficients in A, so A has coefficients in F, so they're all in the field F. And lastly, and most important, the determinant of A is not 0. In other words, A is a non-singular matrix that can be inverted. So we have a property of the determinant which says that the determinant of the product of two matrices is equal to the determinant of A times the determinant of B. This is a property which we will use here in our definition of GL and F. And the GL and F is a set along with an operation which we have is the matrix multiplication that we all know. Together they form a group. And this is what I'll be proving now. So in a group, we have that the set has to be closed under the operation. In other words, if you multiply two elements in the set, you have to have a product which is also inside GLNF. So if we have two elements A and B in GLNF, and we take their product A times B, then we need to verify that A times B is in fact inside GLNF. Okay, so is AB in GLNF? Well, AB is n by n as well, because an n by n matrix times an n by n matrix gives also an n by n matrix. AB has also coefficients in F, because F is a very nice field where both addition and multiplication are closed operations. So these two conditions are met. The last condition is that the determinant of AB should not be equal to 0. But that is easy to verify, because if we take the determinant of AB, we get determinant of A times determinant of B. And since this is non-zero, and that's non-zero, then their product should not be equal to 0. And so we have fulfilled all the conditions so that AB is a member in GLNF, thereby proving that matrix multiplication is an operation under which the set GLNF is closed. So we need to prove that every element A has an inverse for it to be a group. So A has an inverse because the determinant is non-zero, so A is invertible as a matrix, and the determinant of A inverse is equal to the inverse of the determinant, so just the reciprocal by a property of determinants, and that is also non-zero because determinant of A is non-zero because A is in GLNF, thereby proving that A inverse is inside GLNF as well. So we just proved that every element has an inverse. The identity is just the identity I, which is the elements with diagonals on 1 and 0 otherwise, and the determinant of I is always equal to 1, which is non-zero. And the, well, matrix multiplication is an associative multiplication by nature. We've taken this in linear algebra probably. And so the conclusion is that the set of GLNF makes a group, and in fact it is a group we call the general linear group of order n on F. So if we have F, a field, and we have n, a natural number, we can construct the general linear group of matrices with coefficients in F that is n-dimensional. The last thing to cover in matrix groups is three more special types of matrix groups. So starting with the special linear group, SLNF, it is all the matrices A that are n-dimensional with coefficients in F, and the determinant of A, not only it is non-zero, but it's equal to just 1. So whereas the general linear group had determinants that could have been equal to a number that is other than 1, special linear group is just 1. Then we have the orthogonal group, which is denoted by O and F. So O and F is all the matrices in the general linear group, so it is a subset of GLNF, all the matrices in the general linear group such that A times its transpose is equal to the transpose times A is equal to the identity element. And this property only holds for orthogonal matrices. The last one is special orthogonal group, which, if you have guessed correctly, is the group of matrices which lie inside the orthogonal group already, but with the additional criteria that the determinant of A equals 1. And with that, we have completed the topic of matrix groups. Let us now move on to the subject of quaternion groups. To start, we will consider the set of complex numbers. So the complex numbers are, again, the numbers a plus bi, where a and b are real numbers, and I is such that I squared is equal to -1. So I is the square root of -1. It is fairly a standard definition of the complex number c. But what if we have decided to include another distinct square root of -1? So let us do that. Let us include another square root of -1. We call it j. So j is not I, different from I, but also j squared is equal to -1. So what happens then? What kind of set are we going to end up with? So we consider now the set that includes both I and j. So it is a natural extension of c, where we add j here. So it's a plus bi plus cj, where a, b, and c are real numbers, and I square and j square give -1. One of the fundamental properties that we have in complex numbers is to find the norm of an element in C. So the norm is basically a measure of the distance of C from the origin. And in C, we can measure the norm by multiplying the element by its complex conjugate. So this gives us a square minus abi plus abi minus b square I square. And since I square is equal to -1, this just turns into a square plus b square. So it is a very satisfying formula that gives us just real numbers. A and b are real numbers. So what happens if we try to take the norm in the new set that we've created, where we added the j? Instead of just having I, we have now I and j. So let's try finding the norm of an element a plus bi plus cj. So the conjugate of that would logically be a minus bi minus cj. Now the calculation is a bit long, so I'll just skip into after the calculation, and you can verify yourself that it's true. So after having done the calculation, we end up with the formula of multiplying by the complex conjugate to have a square plus b square plus c square minus bcij minus bcji, which is not very nice to have, because whereas we had a square plus b square, which is a very satisfying formula that contained only real numbers, and we were so close to having the same thing with the new set, this is really an annoyance at this point. We really want to get rid of it, so we want to equate it to 0. And how do we equate it to 0? Well, if we equate it to 0, that means this, which is equal to minus bc ij plus ji, and since b and c are assumed to be any numbers, so not necessarily 0, so this has to be always equals to 0. So we really want to say that ij is equal to minus ji for this formula to be beautiful, for us to have a norm that makes sense in this new set. So this is in fact what we're putting. We're putting a relation that says, okay, put I, and we invent j as well, but also put a relation between I and j, which says that ij is equal to minus ji. Now that we've set some ground rules on this set that contains I and j, it's time to formalize some stuff and construct a beautiful group that's called the Quaternion group. So let first k to be equal to I times j, since I times j is so important to us now. So we need to verify that k squared is also equal to minus 1, making it the third square root of minus 1. So k squared is equal to I times j times I times j. We can use the associativity now to say I times j times I times j. And j times I, we have already said. So we've said that ij is equal to minus ji. So we can flip the order by flipping the sign, and we have minus I times ij times j. And now we can have I times I and j times j to be I squared and j squared. And each of I squared and j squared gives minus 1. So this gives us minus 1 times minus 1. And the answer to that is minus 1. So, in fact, k squared is equal to minus 1. And we also know that k is equal to ij, which is equal to minus ji, which is equal to k as well, because ij is equal to minus ji. And minus k is equal to ji, in fact. So, we have now the relations I square equal minus 1, j square equals minus 1, and k square is equal to minus 1. And we also have that ij is equal to k, and it's not equal to minus k, which is ji. So using these relations, we can construct the Quaternion group, and the set of the Quaternion group will contain the elements I, j, and k. So we will put in I, j, and k. But this is not enough to construct a group, because what about the identity element of the group? Well, the identity element is just the element 1, because this set is going to have an operation of multiplication. So it is natural to have the multiplicative identity in the set. So we have that ijk is equal to 1. But what about I squared? Well, I squared has to also be inside the set, and I squared is equal to minus 1, and I don't see minus 1 anywhere here, so I have to add minus 1. Okay, great. What if I multiply I with minus 1? I'll get minus I, and minus I cannot be represented by any of the elements that I have already in this set, so I have to include minus I. But poor j and k, I can't just leave them alone. I have to include their inverses as well, minus j and minus k. And now each element, so if I multiply I by minus I, so I times minus I is equal to minus I squared, which is equal to 1, because I squared is minus 1. And the same with j and k. So each element here has a multiplicative inverse, and the identity is already found and it's closed under the operation, so we can call this a group. In fact, it is called the Quaternion group. And now, instead of just writing this whole set, we can write the Quaternion group in terms of a presentation. The presentations we've already seen in lesson 4 after dihedral groups, where we talked about how groups can be generated with specific relations between the elements in the group. I highly recommend you go back and check it out if you've forgot these ideas a little bit. So the presentation of Q8 in here is Q8 is generated by just I and j. In other words, you can have all of the elements in the set by just combining I and j together. So I is already covered, j is already covered, k is equal to I times j, which are already covered. 1 is just I times minus I. Minus 1 is just I squared. Minus I is just I cubed, j cubed. All of the elements can be covered by I and j. So here we have I and j, but we have specific relations to the quaternion group. We have to have that I to the 4 gives us back the identity. We also have to have that I squared and j squared gives us both the same answer. They cannot have two different answers. And lastly, we have to have that ij is equal to minus ji. Now these, I admit that these relations give a sort of artificial view on things, like how come I came up with exactly these three relations that describe the group? Well, it turns out after some verification that these three relations are sufficient and necessary to provide a complete presentation of the group Q8. In other words, it gives all the information we need to construct the group Q8 from scratch. And with that, we have completed the lesson 6 in group theory. Please like and subscribe if you've enjoyed this content. I highly recommend you check out the previous lessons to learn more about groups and some special types of groups. I will be posting a lot more in the future, talking about all sorts of ideas that we'll be encountering in groups, all sorts of beautiful results in group theory. I'll see you in the next time. Have a nice day and bye.